Okay, thank you very much for the introduction and good morning everybody. First of all, I would like to thank the organization to give me the opportunity to be here and present the work that we have done in our group during these years. So, okay, I'm going to present some results related to the magnetovolume effects in metamagnetic memory compounds. And okay, first of all, I would make an introduction that we already speak about this, the possibility of these Elsler compounds based on nickel, manganese, and then with gallium, iron, indium, a lot of different elements that give us fascinating interplay between the different degree of freedom, and we can play as Dr. Mañosa told this morning with all of different parameters or variables. So this gives us a lot of interesting applications in actuation, sensing, damping, energy harvesting, or also in multicaloric effects. So this is the motivation of our work, try to develop these materials and improve their properties in order to to use them in different applications. We know that in the case of the actuation sensor, these materials present a large strain until 10%, and the important is that this is reversible strain, and these materials present a high frequency operation also, and without contact. That is some advantage. So they are very interesting in different applications for different sectors. And also, that is the point that we are discussing today here. This is very good materials or promising materials for magnetic refrigeration, because they are environment friendly, cheaper, and also more efficient than the nowadays used technologies in expansion compression gases, for example. Okay, so this solid-state refrigeration is based on this magnetocaloric, elastocaloric, and barocaloric effect that we have spoken about this during this morning. And okay, only remember that what is the origin of this magnetocaloric effect, We have this big jump or different of the magnetization when we go from our austenitic phase of high magnetization at high temperature and to the low magnetization martensitic phase. And also, when we apply a magnetic field, we have this shift of the martensitic transformation to the down temperatures, and this is because there is an interplay between the temperature and magnetic field that we apply. As a result, we can get entropy change that is related with this change of entropy of magnetization, and also to the dependence between the temperature and magnetic field applied. Okay, a lot of efforts have been done in order to improve these parameters with different dopings and different compositions. But still, there is some problems in these materials that are inherent to this first order structural transformation that they present, and this is this problem is related with this hysteresis, thermal hysteresis that they present in related to this first order. So this makes us that we cannot have a magnetocaloric effect reversible, and also restricted the interval operation, and as we want these materials to be cycling because for the refrigeration, so we lose this magnetocaloric effect. So different okay, it doesn't work now. Different technical improvements have been proposed in order to overcome this problem. So one of these is to try to use different external stimuli simultaneously or sequentially, as Professor Mañosa explained this morning, with trying to overcome this hysteresis, and also is proposed to to look for new heterostructures in order to try to increase this interval operation of the operation of these materials. So today I would like to focus on this part to try to show how is this external stimuli when we apply different external stimuli, what is the effects on the properties of these materials. And in particular, we are studying the combined effect of the magnetic field and hydrostatic pressure in a prototype nickel-manganese indium, trying to show what is the impact or the influence of the magnetic volume effects using the different this experiment. So for this, we use a polycrystalline nickel-manganese indium that is a prototype, and we're measuring different magnetization curves at different pressures. So it is very clear that we have here our structural transition, but also we have two magnetic transition and the austenitic phase and in the martensitic one. As we expected, the pressure increase the transformation temperature, but the impact is different in the magnetic transition. We can see that in the case of the Curie temperature of the austenitic phase, the pressure increase this temperature, but in the case of the martensitic phase, this temperature is decreasing. We can see here how we have different phases in this phase diagram, going from low temperature, from a ferromagnetic martensitic phase to an antiferromagnetic one, and then go to the ferromagnetic austenitic phase to this paramagnetic. And seeing how, in the case of the pressure, the structural transition go to high temperatures, and also the magnetic transition of the austenitic phase, but in the case of the martensitic one, it goes those. And it seems that the impact of this pressure, hydrostatic pressure, on the structural transition is higher than in the case of the magnetic one. Okay, what is the effect of the combined with the magnetic field and hydrostatic pressure? So in this case, we have opposite influence. In the case of we can see the continuous line is at zero pressure and without pressure, and then we have this discontinuous line that is the effect of the pressure at different magnetic fields. So in this case, the pressure shifts the temperature till high temperatures, but the magnetic field go down. So have a combination at the end. The effect is opposite. It seems that the main effect is the pressure one in this, and the effect of on the magnetization, it seems low of the pressure, but the delta time, the change of magnetization decrease when we apply this pressure. This is because the transformation, the magnetic transformation go close to the Curie temperature, so we lose this jump. In the case of the magnetic field, there is a high influence of the magnetic field on the magnetization, but it seems that there is a low influence of the jump on the magnetic transformation. Okay, we see this in the 3D phase diagram. We can we can see what is the influence of this magnetic field and pressure at the same time. In the case of the temperature of the dependence of the temperature with the magnetic field, we see that there's a linear temperature. We have a delta T versus delta with the magnetic field linear, but in the case of the pressure, it seems that it's not linear, it's a non-linear behavior. And we have a possibility to change this temperature when we apply a field and a pressure of these values. We can change this martensitic temperature. So this phase diagram gives us the possibility to play and and try to work at the temperature that we want. Okay, another problem of the problem of these compounds is this is thermal hysteresis. So we study also what is the influence of pressure and magnetic field in this hysteresis, and we see that in the case of the pressure, the hysteresis decreases, so it's a good option, apply pressure. But in case of the magnetic field, there is an increment of this hysteresis. But in a total, if we play with both parameters, we get a total reduce of this hysteresis. Okay, we evaluate also with this Clausius-Clapeyron relationship the entropy of the system, and without applied pressure, we can see how this entropy is decreasing. That this is the normal that happen in another systems. But when we evaluate this with different pressure, we see that the pressure increase this entropy change. So this is related because the pressure don't have a big impact on delta time, but there is a decrement on the dependence of the delta T versus delta H when we apply this pressure. So in a total, we can see that there is an increment on this. Okay. We speak until now about this structural transformation, but there is also an interesting result that is what is the influence of this pressure on the magnetic transition. So we saw that there's opposite tendency, and the Curie temperature is increasing in the case of the austenitic phase, but decreasing in the case of the martensitic one. So this behavior can fit well with this Castelli-Scanomata empirical curve, and we have here our system that is in the austenitic phase when the pressure increases the Curie temperature, and in the martensitic phase that this pressure decreases this Curie temperature. So until now, different systems, so different behaviors, but we have in the same material one behavior or the other one depending on the temperature that we have. And this can be explained because of this manganese interaction distance. And we can see, for example, that the difference in the austenitic phase and the martensitic phase, there are different distance between the different manganese on our structure. So this makes that this exchange interaction change, and we can have sometimes manganese in one place or in another, one interaction exchange or different interaction exchange, and this make us to have these two different behaviors. This is also explained with this RKK interaction, that if we are in a point where the distance is changing, we can have one behavior or another behavior in this point related with this exchange interaction. Okay, to explain this, we also try to give a model based on this Landau theoretical thermodynamical theory, and for this we suppose that the system is composed by two ferromagnetic sublattices with two different moments, and that these two ferromagnetic sublattices have interact between them antiferromagnetically. To evaluate this theory, we take into account this give energy, and with two terms, one related to this exchange energy and Zeeman energy, and another term that is related with the magnetoelastic energy. So this model allows us to evaluate this magnetovolume effect that can have in these materials. take into account this Landau theory, we can modelize this change on the Curie temperature on both martensitic and austenitic phase. And in this model, we take into account these two different magnetoelastic constants that, in order to fit with the experimental data, must have a difference in this case. The elastic constant related to both sublattice must be positive, and the sum of both must be negative too. And in this way, the theory gives us the correct behavior of our system. With this Landau thermodynamical theory, we can also explain what is the relation or the dependence of this structural transformation temperature with the pressure, depending on this elastic constant, and also with the magnetic field. Okay, this theory and the fit with the experimental results give us to conclude that there is a weak antiferromagnetic coupling between the two sublattice ferromagnetic sublattice that we can model this system. Okay, so to finish, some conclusions, only a summary of this combined effect of hydrostatic pressure and magnetic field in this prototype. So we evaluate this 3D phase diagram. That is an interesting result. The opposite sign of this magnetic transformation in the martensitic and austenitic phases. That because this gives us an idea that there is the system is a complex magnetic systems, and there is a long range antiferromagnetic coupling. Also, we can evaluate some different volume magnetoelastic constants with this model, and finally we evaluate the entropy and the dependence of this entropy with the pressure and magnetic field. Okay, something thanks for the financial, and also I would like to thanks for the group of magnetics and magnetic materials where I work, and also to Jesus Rodriguez of the Universidad de Cantabria and Victor Livov of Magnetics Institute of Ukraine, because they have worked in this. Thank you very much. Thank you very much.
I want to ask you, first of all, thank you for this fruitful talk. You haven't published it yet. Did you publish these results?
Yes.
You published. All right. I haven't seen on the your presentation that you have published it.
Okay, if you want, I can give you this. Yes, but
yes,
we
please,
already published. Yes,
that's quite nice.
Yes.
And the other thing, that your experimental setup for this magneto pressure measurements, how you made it?
Oh, okay, it's a normal UVSM, but then we use this LOAT, LOAT to apply the hydrostatic pressure. It's similar like the other question, I think, during this morning, how apply this hydrostatic pressure. Which is some cells that use some fluid inside, and you can pressure. So we can introduce this in the UVSM. And
is this a commercial setup, or it's purpose-built?
Yes, I think yes.